we want to isolate the radical if it's not isolated already. But technically, the square root is already isolated. And the one extra step that we did was just rewrite that as a 1/2. You don't have to do that step. There's a reason why we did it. Because of this year, we just haven't had a lot of time to spend with radicals, so we're just trying to make that connection early and often. But since it's isolated, we have to raise both sides to the reciprocal power, which is really just squaring both sides. And when that happens, this 1/2 and 2/1, they multiply together to give me 2/2, which is really 1. So I get 9x to the first power. And then we have to think of what does it mean to be squared. And this is something that maybe you want to do as some side work. You have to FOIL x minus 4 times x minus 4. And you can do the box method, or you could use the arrows. Doesn't matter. You might even be used to doing this in your head. If you know the pattern, and you can do all this in your head, you don't have to show any of this work right here. Okay? But if you do all that, you should get x squared minus 8x plus 16. Alright? So then the next step is to move everything over to one side. I like the fact that the x squared is positive, so I'm going to bring that 9x over to the other side. And now I'm looking for factors. I got to factor that if possible. And I don't think we've done one yet where it hasn't been factorable. But if this cannot be factored, you can still solve it using quadratic formula. So I do want you to keep that in mind. However, factors of positive 16 that add up to give me a negative 17x are negative 16 and negative 1. And then when I solve each one of these, you're going to set each parenthesis equal to 0. You don't have to show that work. You can do it in your head. It's just the opposite. What makes this 0? What makes this parenthesis 0? 16 and 1. Now, we'll say that we have to check now, and I'm going to actually show you a very quick way to check. We didn't get to this the other day, but let's look at this one right here. If I plug 1 in here, I'll have 1 minus 4 equals the square root of 9 times 1. Now, without even doing the square root of 9 times 1, let's look at this here. 1 minus 4 is negative 3. If I stop right there, you see a problem with that? What's the problem? Square roots cannot be negative. Anytime you take the square root of a number, it turns out to be positive. So we could have just kind of noticed that if I put a 1 here, you're going to get a negative, and that automatically doesn't work. If I wanted to, though, it's not too bad to actually go through, but notice you end up with a false situation. So in that case, I would identify x equals 1 is an extraneous solution. It doesn't work. And you might be able to do, I'd say I wouldn't maybe do the next one in my head, but if I check 16, I get 16 minus 4. That's 12. So I get 12 equals the square root of 144, which actually works. So that means x equals 16 is a solution that works. So keep in mind, and you may have experienced this with the delta math, that if you do all the work and you don't check it, they're not going to give you credit for it, right? Now, if this was a test, if you said both of these were answers, you would get credit for some of it because you did a lot of work to get that point, but you wouldn't get full credit because you didn't identify the extraneous solution.
Okay, I'm going to need a different slide for this one, so let me copy this. I had a couple people ask if we could just talk about some of these, a problem like this from last night's homework. We'll talk about that test as well. There we go. So you don't have to write this. I'm just going to do it as quick as possible, just so you guys can get some feedback really quick on how we would do this. So we run into one problem here when we have multiple radicals. And the problem is, right now, the right side is isolated, but the left side is not. And no matter what I do, I can't just isolate both radicals. Even if I brought the radical over here, that still isn't isolated because I've got two radicals on one side. So we run into a small problem with this type of problem. So what we're going to do is we're going to just square right away. And what that does is it gets rid of this radical and this square. They reduce each other out. So I'm left with 5x plus 11 on the right side. The left side is where the work comes in. So think of all this as side work. And I've got a square, the square root of 9x plus 1. Now, you could FOIL, but to be honest, I think students are going to be a little better with the area model here. And then we're just going to multiply the areas together. Now here's one thing. For this box right here, what are we doing? We're multiplying the square root of 9x by itself. Right? We're squaring it, or timing it by itself. Isn't that the same thing as squaring it? And since that's the same thing as squaring it, doesn't the square root and the square reduce out? So I'm left with a 9x right there. Alright, and then here when I times by 1, that doesn't change anything. And then when we times by 1 there. But I do have like terms here. And remember, this is a 1 square root of 9x plus a 1 square root of 9x. So if I added all those boxes together, it would turn out to be 9x plus 2 square roots of 9x plus 1. That, I think, is the hardest part right there, getting to that. Because now, I know it doesn't look like we did much. We actually kind of made it look more confusing. But look at this statement. How many radicals are left over? We have 1. Now think of this as a brand new problem. Your goal now is to isolate this radical, the square root of 9x. So now we're just going to do a lot more algebra. And I'm going to bring that 1 over to the other side. And at the same time, I'm going to bring that 9x over to the other side. So both of those go away. And I'm left with basically a new expression. And again, our goal is to isolate the radicals. So I now have to get rid of the 2. And I'm just going to divide every single piece by 2. And now we get to a place kind of similar to our wormhole. I have a squared. Again, we could write this as the 1/2, but what we're really going to do to get rid of a square root, we're just going to square both sides. So I get 9x over here, and then think of this as maybe more side work. You need to FOIL that out. So I get a positive 4x squared minus 10x minus 10x plus 25.
So we get all of that. And then we run into that same situation we just had. Move everything over to one side. And then we have to factor. Right? Now, I'm not positive. Nothing jumps out at me right away if factoring is going to work here or not. I'm going to try it, but if it doesn't, then I'd have to do the quadratic formula. So we'll multiply our two corners. And I'm thinking, what are the factors of 100 that add up to give me negative 21? And that's 4 times 25 is 100, so they're both negative. And then we'll pull out common factors. This is an interesting one because, well, actually, no, not really. If I pull a 4 out there and I pull a 25, but I want it to be negative, what's left over here has to be a 1 and a negative. So again, double check that that actually works out. And it should. I don't think I made any errors. And then you can set each one equal to its own 0. So what I would do here is I'd add 25 and then divide by 4. And as if we haven't filled up a full page of work already, are we done? What do we have to do now? Now you're going to check, right? So I'm going to grab that equation. Bring it down here. And unfortunately, we don't have any subtraction or negative, so I can't use just a quick thing to see if this whole side was negative, then we knew it wouldn't work because of the square root on that side. So I'm going to, 1 is easy to check. I might do that in my head. 1 times 9 is 9. The square root of 9 is 3. 3 plus 1 is 4. 1 times 5 is 1 plus 11 is 16. 4 equals 4. So I know that x equals 1 works. Now let's do the same thing with 25. Works. Unfortunately, this isn't super friendly. There's some tricks we could use to help simplify. One of the tricks is if I just take the square root of everything individually, that would be 3 times 5 halves, which is 15 halves, plus 1. But if I drop this 1 down, I might call 1 2 over 2. And the reason why is because then I can add my fractions together. And again, you can use your calculator. You don't need to do all this by hand. Right? And then this one doesn't work as well. So then I'd have 125 over 4 plus 44 over 4, which is 169 over 4. And then all of that's still over that square root. I take the square root of the top and the bottom. And that's 13 halves. So that doesn't work, which we can abbreviate that as extraneous solutions. That's a lot. And I might say this right here is probably the most amount of work that you're going to do for a problem in this class this year. I'm not 100% confident on that, saying that, but I know it's close. Okay, really quick, I just wanted to
let you know there were, I think there's 5 people who still have not taken the Chapter 5 test. If you're one of those 5 people, get that done today. I'd like to grade that and just have your grades up to date as much as possible. You can view this now. If you open up the test, you can see which problems you got right and wrong. If the test did not go your way, remember you can do corrections on a separate sheet of paper, correct anything you got wrong, and just email them to me, and then I will give you 70% back, so you could boost your grade to a 70%. Okay? All right. This might be perfect for that last problem we did. Patience is the key to contentment. We are going to start with this whole idea of functions. And we're going to start with something called function notation, which we've seen and hinted at. And you'll notice that really these problems we've done before. So I actually don't think you need to write any of the words here. What I'd like you to do is try these 3 problems. If I tell you that f of x is the equation 3x squared plus 7, and g of x is the equation negative 2x plus 1, I would like you to find the difference. I'd like you to find g minus f. And then I'd like you to find the product, f times g. And then I'd like you to find the square of g squared. So we just haven't done a lot with this idea of combining functions. And we did the actual addition, subtraction of all this. I'll just set up the first one for you, just so you know exactly what to expect. But it tells me to take g minus f of x. All you're going to do is replace g with what it's equal to, and replace f with what it's equal to, and subtract. So just so I know you're on the right track, the only hint I'm going to give you is you can kind of think of everything as being in parentheses. And that way you won't make any issues with this subtraction. Okay? So then try that. Try the multiply and try the square, and we'll give you a couple minutes just to work through that quickly. Alright, so I'll just kind of get this set up. With subtraction, I don't like to think of it as subtraction. I like to think of it as adding the opposite, and that's usually where an error occurs. Now we just got to look at combining like terms. I have a negative 3x squared, and then I have a negative 2x, and then I've got 1 plus negative 7, which is negative 6, and that's as far as we're going to take that. And then it says, the next one is do f times g. Well, that's multiplication. So we could write that as 3x squared plus 7 times negative 2x plus 1. Now you can do the arrows here, or you can do the box. Whatever works best for you. Since I set it up this way, I might do the arrows. I get negative 6x to the third plus 3x squared minus 14x plus 7. And then there are no like terms this time. So I can't add anything, which means if you did your box, you didn't have any like terms, and that's as far as we can take that one. And then the one that depends on how you want to think of this. Technically, all we're doing is replacing g of x with what it's equal to. Then we're going to square it. Now, here's one of the issues. I haven't brought this up yet, but I want you to be careful. You cannot just square each term inside, and that's usually an error we see. You have to think about, what does it mean to square something? It means to multiply it by itself. So I really hope when you see that exponent, you're thinking the meaning of the exponent. And then it's FOIL multiply. So I'll use the arrows again. and as far as we'll take that. So hopefully you're thinking, well, didn't we just have a unit on this? Adding, subtracting, multiplying, polynomials? Yeah, this was chapter 5 right here. The only difference is instead of giving you guys the equations, we call it f of x and g of x. So now we're using what's called function notation. It's just a different way of representing the same things you've already been doing. But there's a twist. There's a new part, and it's called composition of a function that at times kids can really struggle with. One of the things I've noticed in my pre-calculus and calculus classes is this next concept is something kids don't grasp fully. We have to review it multiple times. So I'm going to start off with this piece. I do not want you to write it. We're going to talk about evaluating functions, and the key idea is to think of this as like a machine. All right? So, like I said, it's not worth you guys writing this, but what if we keep the same f of x and g of x? Right? When you see f of x, I want you to think 3x squared plus 7. When you see g of x, I want you to think negative 2x plus 1. So what if I tell you to evaluate f of 2? Well, what does that mean? When you see a number inside of the parentheses, notice that's where the x is. We're telling you to put a 2 there. So what happens is x equals 2 goes into the function f. Something happens. It happens by the rule. So what happens is we take the x, we square it, and then we add 7. Okay? So we do proper order of operations. So 2 squared is 4. 4 times 3 is 12. 12 plus 7. And what happens is we get an output. Now it's important to think the 2 is the input. That's what goes into the function. The 19 is the output. Okay? And I know you're thinking, Strub, that's just evaluate. Right? This isn't the hard part. This is the part that we hopefully are comfortable with. So maybe you could do this one in your head. What if we tell you to evaluate g of 3? Input goes in. Something happens, because it's g, so we do whatever g is programmed to do. Oops. And then something comes out, right? So we get negative 6 plus 1. My input is 3, my output is 5. Now, the twist, here's the new part, is what if I tell you we have the exact same things. I can never find this. There we go. But now, I want you to apply the function g, which I'll write this here, so I don't forget it. What if I tell you to take that answer, that output that we had, so we're going to take f of 2, which, by the way, this is f of 2. F of 2 is 19. Now I want you to take the output, and that goes into the function as my new x. So we're using the output from the first answer and applying it now in the function g. So we'll plug 19 in. Let's see, negative 2 times 19 is negative 38. Plus 1 is negative 37. Now the question is what did we just find? Well, it's 2 parts. We did 2 pieces here. The first piece that we did was f of 2. But then we took f of 2, we took its answer, and we plugged it into g. You see how f of 2 is in the inside part? And then we took that answer and we applied it to g. That's called a composition of a function, when you use one function inside of another to produce an answer. So let's look at this one quick. What if I have g of 3? X equals 3 goes in, negative 5 comes out. And it's important to know that this answer is g of 3. So what if I tell you now to take this answer and plug it back into g? So I'm doing g and then g again. Well, what's going to happen is the answer of x equals negative 5 goes back into my function, and we know what g is. G is the equation 2x plus 1. But now my x this time isn't the original x we started with, it's the output, it's the answer from the first one. So that'll be a negative 5. When I plug that in, I get 11. And where did that come from? Well, the first answer we got was g of 3. So I did g of 3 first, and then we applied g again. So this would be g of 3. Oops. That should be a 3. And that's the idea of this function notation, when you have a function inside of a function. Now, it's not horrible when you're just dealing with numbers, right? Because you basically plug 3 in, you get an answer. Take that answer, plug that answer into the new equation, and you get another answer. But what if we don't plug in 3? What if we just plug in x? And that's where it gets a little more challenging. So, I forgot about this. You don't have to write this either. There's a question on Delta Math tonight that looks like this. And what it gives you is it gives you 2 graphs. Here's the graph of f on the left. Here's the graph of g on the right. And they're going to ask you to find g of f of negative 4. So how we're going to approach this is, some people like to think of the movie Shrek when you're doing problems that are like this, because these are like onions. What do you know about onions? They have layers, right? Now, the weird part about that is we're going to start with the inner layer. We're going to start with f of negative 4. So I now have to figure out what is the answer to f of negative 4. Well, that's a graph. Okay? Here's the graph of f. What is f of negative 4? I'm going to go over negative 4. Here's negative 4, but where does it hit the line? That's not the best picture. I think it's negative 1. It looks really close, negative 1. I'm going to say that's negative 1. So now, notice, its answer, f of negative 4, has an answer or an output of negative 1. But now that goes into g. So now I have to apply the outside function. See how that outside layer appears in green? We take the answer to the inside and apply it now to g. So now I have to find g of negative 1. So here's negative 1. We're going to go down, and that has an output of negative. So the only other thing I threw in here was a different type of notation, f of 2. So it can be written with the layers, or it can be written as f of 2. When you see f of 2, you can rewrite it like the other one. So what I'd like you to do, I know it's not super easy to see this from where you're at, but go ahead and try these 3. You don't have to write it down if you don't need to. Just see what you get. So much easier when you actually have it in front of you versus doing it from a screen. Well, let's just take a look at kind of the idea of the layers here. So if I want to find g of f of negative 9, I'm going to deal with the inner part first, and I'll go and find what is f of negative 9. So here's the function f. F of negative 9 looks to be right there at 4. So then I'm going to think, all right, what is g of 4? So then I go to the graph of G. Where is 4? What is its output? G of f of negative 9 is 2. Okay. If I do the next one, deal with the inner part first. So f of g of negative 5. Now g is the inside layer. We're going to go over to negative 5 on g and see that its output is at negative 7. And then I'm going to do f of negative 7. So then I have to go over on f. Where's negative 7? It's up here at 8. And then the last one is if I have f of 2, that's telling you to do f of 2. So I'll go over here. Oh, shoot. We can't do that one. Sorry. Let's change that. How about f of negative 5? Let's see if that'll work. I think that should be fine. I'll have to fix that on the note. So f of negative 5, or f of negative 5. So what is f of negative 5? Here's negative 5. We know its output is 4. So then that's telling me to do f of 4. So I'm going to go, shoot, can't do that one either. Okay. I can't do f of 4 because notice here's 4, and that's not on my graph. I should have checked that carefully, but I think you guys get the idea. If it's f of f, you're using the same graph twice. Okay. So let me show you what this would look like if we use x. And we're going to think of this as a machine, right? Notice f and g are the same thing as they were before. So what if just x goes into my function f? Well, what comes out? What comes out is the equation itself. 3x squared plus 7. Okay? So nothing special there. But what if I now tell you, there it is, to apply that to g? So now we're going to take our answer to f, and that goes in as my new input. And one way to think of this is now I have to take whatever g was, which is negative 2x plus 1, and instead of thinking of it as an x, we're doing negative 2 times whatever the input is. So this is the new input going into that function. And watch what happens. I do negative 2 plus, or excuse me, times whatever the x is. So that whole equation is now my x. And now we have to simplify, which I don't love how small that's written, so this is really the work that we're doing. And now we just simplify. So I would distribute the 2. I get negative 6x squared minus 14, the plus 1 drops down, and 13. I don't end up with a specific answer. What I end up with is a new equation. And that new equation is what f of g of f is. G of f of x. So what was the inner layer? The inner layer was f. The outer layer is g. And now, instead of doing just f, if I wanted to evaluate a point, I don't have to do it in 2 separate steps. I have the answer all condensed. I can just plug in 2 into that equation. So now that's 4, negative 4 minus 13 is negative 30. So let's look at what I want you guys to write down now. So this is called function composition. If you guys would title it function composition, it can be f of g or it can be g of f. It can be written in multiple different ways. And that means we're going to find the answer for g and then use that as the input to evaluate f of x. We're going to use the same f and the same g that we used all day. But this time we're not going to do it with the whole function box, like that image of a function going into a machine and something happening. We're going to just do it the efficient way. So let's first find f of g of x. And if you want to make that little note, that little math symbol stands for the word of. But I really don't love this notation. When I see f of g of x, I rewrite it like this. And if you're somebody that likes to use multiple colors, this might be the time to mimic my color scheme. So my goal is to find a new expression for f of g of x. Well, all we're going to do is replace the inner layer first. What is g of x? G of x is the expression two x plus 1. Notice that's my new input. And then we're going to use that as the new x value into y. So remember how we can think of x as the input? We're not plugging one number in, but we're plugging a new equation in. So I'm going to take 3 times x squared plus 7, but my x is the input. It's the entire expression, negative 2x plus 1. And now, everything else is algebra. So, hopefully, if you can understand what we did up to this point, that's the new part today. Everything else is just simplifying. But we do have to be careful, because the simplifying side, we have to think of what does it mean to square. It means we have to take negative 2x plus 1 and times it by itself. So you can FOIL here, you can do some side work. If you can do this in your head, perfect. I'm going to do a little bit of side work though. And I'm just going to FOIL out that blue part. I did it pretty quick, but I just FOILed it out, and then I had my two middle terms as my like terms. But notice that 3. Now the 3 in the parentheses are key. Right? That 3 has to be distributed to all of those terms. And then we simplify as far as we can, and we get a new expression for f of the of x. So why might that be important? That just seems like a math trick, right? Well, what it actually is if I want to figure out, like let's say I want to put x equals 5 in. What you could do is you could plug 5 into g first and get negative 10 plus 1 is negative 9. And then plug negative 9 in here. You get 81 times 3 plus 7, and you get the answer. Or, now that we have the equation, you could plug 5 in here and do it all in one step. And that's the benefit to composition of functions, is it just eliminates the multiple steps and it puts everything nicely into just one problem. Alright, so what if we flip it around? I want you guys to try this one, but instead of, this isn't goth, this is g of f of x. F is the inner layer, and I'd like you to just try that and let me know what you get when you do g of f. Okay, so g of f of x. Now, f is the inner layer, so we're going to go up and say, well, what is f? F is 3x squared plus 7. And then we're going to take that. That is my new input, and it is going to go in here for the x. So then I write the function g, which is negative 2x plus 1, but in the spot where there's an x. That's where my new input goes. And then it's just simplified. The nice thing here is we don't have any squared, so then I just have to distribute the 2. So I'll get negative 6x squared minus 14 plus the 1. And my expression, g of f of x, is better written as negative 6x squared minus 13. Okay. Once you get used to the notation, it's pretty friendly and kind of fun. All right, so we have one last concept that we're going to talk about. And this you've done from Algebra 1, so we're not going to spend a lot of time on it. And I actually don't want you to write this part here. It's technically, if you're following along in our textbook, it's section 6.4. And it's talking about the inverse of a function. All that inverse does is interchange the input and the output. Well, wait a minute. It means the input is the x and the output is the y. So we're just going to interchange them. The inverse asks the question, if I know the y value, what is the value of x? So if I know y equals 3, what is the value of x? Instead of doing all the algebra and solving, we can do what's called an inverse equation and write an equation in terms of x. So I don't want you to write this, I just want you to watch how it happens. Right? What was an inverse? It was when we switch the x and the y. Here I don't have a y. I have a function. We can rewrite that function as y equals. All right. Now, that's a regular function. It's written in terms of y. I want the inverse, which is written in terms of x. So what we're going to do is literally switch the location of the x and the y. And I'll give you a little more formal notes on this, but we're just going to switch them and now solve. So now I have to solve for y. So I got to add 5 over here. I'm going to get x plus 5 equals 1/4 y to the third. And then I have to get rid of the 1/4, so we're going to multiply by the reciprocal, which is just 4. And you could FOIL here, or you could leave it.
It's up to you. If I FOIL, that's friendlier. And then I have y to the third. Well, as we just saw yesterday, to get rid of the third power, we raise it to the 1/3 power. And you could leave it to the 1/3 power, or you can say, you know what, that 1/3 power is really the cube root. There's only one little thing we do here. Because this isn't the original y that we had before. This is a new function called the inverse. So that little sign there is a -1. That's an inverse. Okay? Now I know you're not super comfortable with that, so I want you guys to try this one with me. Write this one down, and then look at the notation. They say find f of -1. That's telling us to find our inverse. And I'm going to give you the hint. What do we do? There's 2 steps. And again, we'll do this one together. To find the inverse, we switch the x and the y, and then we solve for y. And then we call the answer either y inverse, or if it's written in f terms, f inverse. So those are basically the 3 steps that we're going to do. So, first thing I do, remember that's the same as y. F of x is y. It's the output. So what we're going to do is we're just going to switch those. We're going to switch the spot of the y and the x. So now I'm going to write x is equal to 3 times the cube root of y minus 1 plus 10. Just literally switch the position of x and y. Now we're going to use whatever algebra we need to solve for y. So the 10 has to come over. We're doing it backwards of PEMDAS. So instead of multiply, divide, add, subtract, we go backwards. Add or subtract first. So in this case, this plus 10 is going to come over here as a minus 10. You don't have to show this stuff, but move the 10 over with subtraction. And the next thing, we're going to divide by 3 or times by the reciprocal. Okay? Dividing by 3 is the same as timesing by 1/3. And then that's going to get rid of the 3 and the 1/3. And then I'm left with whatever's in the parentheses. So now, the 1 has to move over with addition. And you could distribute the 1/3, or you could leave it. But I'm going to add 1 over here. And now the very last thing is, remember how this was the cube root? That's the 1/3, so to get rid of it, I'm just going to raise everything to the 3rd power. And our goal here isn't to do a ton of algebra work here, so I'm completely happy with this answer. 1/3 x minus 10 plus 1
to the third power. And then that's going to equal y, but instead of calling it y, we're going to put the little -1 up there for the inverse. So that's all you're doing, and it might take a little practice to get really used to it, but you're just switching the x and the y, solving for y, and then once you have that y by itself, we're calling it y inverse. So homework tonight is delta math, and we did that so you guys can kind of get a chance to check your answers and get some feedback as you go. And it's titled Inverse and Composition of Functions. So. All right, have a good day, everybody on Zoom. Enjoy the sunshine.